Okay, so today we will talk about another form of bifurcation which is called Hopf bifurcation. Okay, so in this bifurcation the system will have eigenvalues, purely imaginary eigenvalues plus minus iota omega naught, and omega naught is greater or equal to 0. Now we do have the normal form. Okay, so in this case n is greater or equal to, the dimension of the system will be 2 or greater than 2. So the normal form, the equation that we do have is actually x dot is minus y plus x alpha minus x square minus y square, and y dot is actually x plus y alpha minus x square minus y square. Okay, so if we see the Jacobian, the linearized part of the system at x is equal to 0 0, because clearly x is equal to 0, y is equal to 0 is an equilibrium point. So then we can have that this is alpha and this is minus 1. So definitely this is 1, this is alpha. And now we know that what kind of the eigenvalues it has. Okay, so we can easily find the eigenvalues of the system, and because it is not difficult, so I'm just writing down the eigenvalues. Lambda 1 2 is actually nothing but alpha plus minus iota. Okay, so surely it has complex eigenvalues. Now to discuss the stability or to discuss the bifurcation of this system, what we need to do, we need to convert this system into polar coordinate. Okay, polar coordinate. So surely then we will say that let r square is actually x square plus y square, and theta is actually tan inverse y divided by x. So once we put everything and we do little bit algebra, so what we will get, r dot is actually r alpha minus r square, and theta dot is actually 1, and this tells us the direction, clock or anti-clockwise, clockwise or anti-clockwise. Okay, so now to discuss the stability we will focus on r dot is actually r alpha minus r square. Surely r is equal to square root of alpha is an equilibrium point of the system. So to discuss the stability, what we will have, f of r is actually alpha minus 3r square, which is alpha minus 3, okay, alpha minus 2 alpha, this is lesser than 0, so stable. Okay, and we know that r is equal to alpha is actually a circle in the polar coordinate. So now what, okay, so if, okay, it might be the case that alpha is 0. So if alpha is 0, what is my equation? My equation will become r dot is actually minus r cube. So the system is stable. Okay, so now if you want to find the diagram, okay, so in case of alpha is equal to 0, okay, so definitely my system is going to be stable. So if I start from here, I will approach to the origin. Okay, I will approach to the origin. Okay, because now since theta dot is equal to 1, so my direction is anti-clockwise. Okay, and surely if alpha is lesser than 0, then we will see the linear part, and again if my alpha is lesser than 0, the linear part is r dot is equal to alpha r alpha, so it is negative again, so it is stable. Okay, so all is less than 0. So again, if I start from here, I eventually will approach to the origin just like in the above. Okay, but now the interesting case is the next one. So for r is equal to alpha, since this is a circle, okay, so suppose if this is my circle, okay, now if this is my circle and this is stable, so this means that if I start, okay, if I start from here, I will approach to the boundary of the circle from the inside, but I will not touch it. Okay, I will not touch the boundary, but I will approach the boundary. So if I start from here, okay, so from the inside, so but from the outside, if I started from the outside, I will approach the boundary of the circle from the outside. Okay, but I will not touch it. Okay, so you can see that I'm going. Okay, so this is when alpha is positive, so we can see that the system is stable. Now to actually draw the bifurcation diagram, okay, bifurcation diagram is very important. Okay, so in bifurcation diagram, surely we have alpha, and on my horizontal vertical axis I have r. Okay, so surely r is equal to alpha is this thing, so this is stable. Because it is stable, so that's why it is solid line. Okay, stable. But now if we see that, okay, if we see that, because our equation was r dot is actually r alpha minus r square. Okay, so on my alpha axis, okay, over here, what is 0? R is 0. So excuse me, so if my r is 0, this means that the non-linear part of r is 0, because I will linearize the system. So definitely if I will linearize the system, r is equal to 0, so this will have alpha. Okay, so over here the non-linear part will become 0, so the linear part will have alpha. So if alpha is positive, my system is unstable. Okay, my system will have, so will be unstable, so this will like this dash. Okay, when alpha is positive. Over here, if my alpha is negative, it is stable. Okay, so this is stable and this is unstable. Okay, so we will just see the linear part, not the, because the non-linear part, when we will linearize it, it will be 0, so we will have just alpha. So this means that if you want a clear bifurcation diagram, okay, so this is, suppose my this was alpha, okay, and this is, okay, so this is alpha, this is r. Okay, okay, so stable, unstable, and this is stable. But over here, surely alpha is positive, alpha is negative 8, r is actually 0, 8, r is actually 0. So this is called, this is actually bifurcation diagram. Thank you, and that's what we had for today.